So we've talked about the implication, the conditional, and we've talked about modus ponens, which tells us something about the structure of a proof. We haven't got to proofs yet. We're doing a little bit more logic so we can get some nice definitions down and so that we can prove some interesting things. We just have to do a bit more logic before we can get to that. So just bear with me through another one of these little videos, one or two, and then we'll be into proving things fairly quickly. So let's talk about these statements that are related to the original implication. Okay? The converse, the contrapositive, and the biconditional. So the converse and the contrapositive are derived from an implication. So given an implication P implies Q, by swapping the order of the hypothesis and conclusion, we form the converse. So converse is Q implies P. The contrapositive, however, is produced by negating the hypothesis and conclusion and swapping them. Okay, so not Q implies not P. And if we take a look at the truth table of these things, you'll see that the converse is definitely different from the original implication. In particular, is a different truth table. So it's not a similar statement. I mean, it has the same sort of flavor, but it's not logically the same. So in particular, when we swap P and Q around to form the truth table for the converse of the implication, has the effect of swapping these rows of our truth table. And so now these two statements, the original implication and the converse, have different truth tables. They're true and false at different times. Okay, so they're not equivalent statements. So we have to be very careful not to confuse an implication with its converse. They're different. On the other hand, if we do things carefully here and write down the truth table of the contrapositive, where we've swapped the hypothesis and conclusion and negated them, then if we're careful, we'll see that it has the same truth table as the original implication. And this is a very useful fact. The fact that this implication and its contrapositive have the same truth tables is something we can exploit later on, because sometimes the original implication is difficult to prove, but the contrapositive turns out to be easier. Okay, so this is a useful thing that we'll make use of later on. So let's think of this as some simple examples, as to get it really clear in our mind why the converse and contrapositive are interesting things. So let's take this simple statement about Shakespeare. If he's Shakespeare, then he's dead. Okay, Shakespeare lived a long time ago, he's definitely not alive. Well, if we form the contrapositive of this, well, if we find someone that's not dead, right, if they're alive, then they're not Shakespeare. Okay? This has the same meaning as this. So the contrapositive here, this contrapositive statement has the same meaning as the original implication. On the other hand, if we look at the converse of the original statement, if he is dead, then he is Shakespeare, well, this is definitely not the same thing. I mean, Elvis is not alive, and Elvis didn't write lots of sonnets and plays. Okay? So this is a handy little way, this silly example of Shakespeare and death, is a handy way of thinking about the converse and the contrapositive to make sure they're clear in your mind. Now, the converse is an interesting thing. It's often a source of very bad logic. So, for example, artists are misunderstood. I'm misunderstood, so I must be an artist, is an example of bad deduction involving the converse. Okay? So be very careful to keep these things separate and straight in your mind. The contrapositive is very similar. It's logically equivalent to the original implication. The converse is not. Okay, so let's look at the converse a little bit more, though. So we have a statement here, if n is even, then n squared is even. Okay, this is a statement we'll prove, and that's basically the first thing that we prove in one of these little videos. Well, once we have this, and we know the converse is different, I mean, this is kind of obvious. If I take 2 and I square it, I get 4, that's even. I take 4 and I square it, I get 16, that's even. Well, it makes sense to also ask if the converse is true. I know the converse is different, but somehow it has a very similar flavor to it. And so if I flip this around, if n squared is even, then n is even, we should ask ourselves, is this true? We know it's not the same as this, but it might still be interesting. And indeed, a great deal of interesting mathematics comes from considering whether the converse of some interesting statement is also true. Okay? This is often very, very difficult to prove one of these two directions. So if n is even, then n squared is even, that's pretty straightforward. If n squared is even, then n is even, that's a bit more difficult. Now, okay, once you've done a little bit of proving things, it's also straightforward, but initially it's a little bit more difficult. So many interesting mathematics statements and mathematical results come from considering whether the converse is true as well as the original implication. Now, one last thing. It's often the case that both the implication and its converse are both true. And we would like to state that in a nice logical way. And we do that with something called the biconditional. So the biconditional is the statement P if and only if Q. And we write this with this double arrow to indicate that, well, this implication going this way is true, and this implication going that way is also true. Okay? So it's a very useful bit of notation. And it's often written also as P if with a double F Q. So P if and only if Q. And the biconditional is true when both P and Q have the same truth value. That is, they're both true at the same time and both false at the same time. And if they have different truth values, then it's false. And so we can summarize this in a table here. Here's our 4 possibilities: true, true, false, false, true, false, true, false. These are all 4 possibilities of P and Q's truth values. Here's the implication. P implies Q. Notice it's false here. Q implies P. Notice it's false here when the hypothesis is true and the conclusion is false. And we then just take the conjunction of these 2 things to get this truth table. True and true is true. False and true is false. True and false is false. True and true is true. And so this statement is true when P and Q have the same truth value, and false when they have different truth values. And this is a very useful little object. Again, we'll come to it as we do more examples. We'll stop there.